All right, so we have a problem. The brightness constraint equation gives us more unknowns than equations, more directions to move than we have pixels. How are we going to recover the motion? Obviously, we need some extra constraints. We need some additional constraints. So we'll talk about sort of a global approach now, and the next time we'll talk about a more local approach that actually is used, and in fact, some of you may even implement. Sometime long, long ago in a galaxy nearby, Bertolt Horn and Brian Schunk did some work on what was called smooth optical flows. And basically they said, let's try to come up with an optical flow that minimizes some error. Okay? So the first part of the error is how much do we violate the brightness constancy constraint equation, right? Basically, that middle term right there, that's supposed to be 0, right? Ixu plus Iyv plus I sub t is equal to 0. So violations of that mean that it's not 0. Sometimes it's positive, sometimes negative. I square it and I sum it up over the whole image. That would be how bad my flow is with respect to the constraint equation. All right? But we know we can solve that exactly because we have more unknowns than constraints. So if that's our only constraint, we're not done. But we're going to call this the constraint error. By the way, I kept partially, originally I had stolen, then I did it on my own. I kept the integral signs instead of summations because back when this work was done, we'd like to think about images as actually continual functions. Of course, if you were to implement this, you'd actually have to do summations. I will also tell you the fact that summations are not integrals matters. And if you take a look at some of the work that was done in shape from shading, doing it as an integral was actually hard. Doing it as summations was in some sense a little bit easier. But for here, the difference doesn't matter, so I just wrote it as being summed up over the image. So here we have our optic flow constraint term. Now we need another term. Well, it says smooth optical flow. Here's the idea. Remember when we did stereo, the state-of-the-art solution that I showed you that did that beautiful recovery, used a bunch of terms, some that had to do with the data, but it also had to do with the smoothness of the disparity field. That was the idea that surfaces don't change a lot all over the place, but they tend to have a particular depth or vary smoothly. The same could be said of motion. That is, so if I've got something moving around, the motion vectors from one point to the next change slowly. So let me come up with a penalty term that says I really don't like velocity fields where the velocity changes quickly from one location to the neighboring location. So that's shown here. These ux, uy, that's the derivative of u. Remember, u is the x component of the motion field. The derivative in the x direction squared, because it would be positive, negative. Derivative in the y direction squared. Same thing as here, which is v sub x, v sub y, the change of v as you move in x, the change in v as you move in y. Again, everything is squared. So the idea is we would like this thing to be like 0 or as little as possible. By the way, what would it mean for this to be 0? Well, for this to be 0, that would mean that all the u's were constant, right? They were all the same value, so the derivatives would be 0. And all the v's would be constant. So if all my pixels were moving with the same UV, the whole image was moving the same direction, this value would be 0. Any other u's and v's will cause this term to have some value, and we want to try to minimize this thing. So now we have these two terms. We have the constraint equation error term, and we have the smoothness error term called E sub c, E sub s. And what we want to do is we want to find the UV at every pixel, and there's going to be a different UV at every pixel, that minimizes this total error, which is just the smoothness term plus some weighting factor times the constraint term. And the weighting factor is sort of how much you believe your data. So the bigger the weighting factor is, the more important the satisfying the brightness constancy constraint is. The smaller the weighting factor, the more the smoothness term dominates. And what value it should have is a function of sort of how much noise there is and how smooth you believe the entire thing is. So this was part of a general approach, variational approach, where you're going to solve for UV as a function of XY. That is, you're going to find the optic flow, U and V, for every pixel that tries to minimize this error. It's somewhat painful to try to implement systems that can solve for that, not impossible. But the idea is that you have a global constraint, the smoothness constraint, to help solve your problem.